Most of you are not from Nagpur, right? So you try going out and checking out the city. Good day. It looks like when it rains, it sort of pours here. It's not a light drizzle. Vancouver, it rains a lot, but it's usually a very light drizzle. You can just walk in the rain. You don't get all that wet. You have a light jacket you can manage. You don't need to carry an umbrella. But here it looks like it rains. When it rains, it pours. So you need an umbrella. All right. So I think we paused at the trade-off between variance and bias yesterday. I spent quite a bit of time describing what bias is and what variance is. Hopefully that gave you a good intuition into what those two errors are. And that's very important. When you're trying to build models, you really need to understand what variance of the model is and what the bias is, right? And your goal often is to find that right balance between the variance and the bias. Today I'm going to just wrap that topic up, and then we'll spend maybe half an hour to 45 minutes talking about the importance of visualizing your data. You don't want to just get the raw data and feed it to machine learning algorithms, right? So that would be not ideal. You want to look at your data, you want to understand your data. And often there's a lot of information in the data that you can extract even before using any machine learning tools. Okay. I'm going to show you a couple of examples of data visualization that we have worked on over the years to emphasize the importance of data visualization. Anytime you get data, try to visualize it in different ways. Often you can reduce the dimensions and plot it to extract useful information. All right. And then after we finish the data visualization module, we're going to look at classification and clustering in the afternoon. If we have time, I'm going to move on to dimensionality reduction. If not, we're going to cover dimensionality reduction tomorrow, dimensionality reduction and regression tomorrow. And then on Friday, I will spend some time on reinforcement learning. Okay, so that's the approximate plan. Okay. All right. You've seen this curve yesterday. It's not exactly the same, but I think what I drew yesterday looks very similar. This is the bias variance trade-off curve. On the x-axis, you have model complexity. On the y-axis, you have the prediction error. And as you go this side to the left, you have high bias, low variance. As you go towards the right, you have low bias and high variance. Now, when the model is too simple, meaning you have high bias and low variance, you're in the underfitting region. So you're underfitting the data. So I have some example of data here. I'm trying to fit this data. If your model is too simple, in this case it's just a linear straight line. You can obviously see that it's not fitting the data really well, and you have this scenario where you're underfitting the data. Okay. And when you underfit data, you get high training and validation errors. Both your training and validation errors will be very large. Okay. Now you can increase the complexity of that model. This is a very simple model, a linear model. You can increase the complexity of the model through the validation process. I talked about the loop, the training and validation loop. So you can go through that loop and increase the complexity of the model, which will in turn reduce the validation error, and hopefully you'll find an optimal model with optimal model order or model complexity. So as you increase the model complexity, you'll find that your validation and training errors are getting better, okay, so which means you're reducing your bias errors. But you can increase the complexity further beyond that sweet spot that I showed you yesterday, in which case you might end up overfitting the data, as shown in this graph here, right? So when you have data like this, often these small fluctuations are due to noise in measurements, and you don't want to capture the noise in your model, because that the capturing noise in your model is overfitting, right? So you don't want to overfit. If you overfit, when you get a new set of data, the errors are going to be significantly larger than what you found when you trained the data with the overfitted model, right? So you understand the difference between these three figures? Low complexity, simple model, training and validation errors are very high because this model is not complex enough to describe your data. You can increase the complexity, add more terms to your data, to your model, and get a much better fit, and therefore reduce the training and validation errors. You can increase the model complexity even further, and when you do that, you'll end up capturing the noise characteristics as well. And noise is something that changes from experiment to experiment, and therefore you don't want to treat that as part of your model, right? So noise is you don't want your model to capture the noise because it's going to change the next time you conduct this experiment. So that's overfitting. Any questions on that? Now, once you pre-process your data and once you train or validate your data, you have to assess the performance of your model. Okay? Assessing the performance of your model is very important. There are many different ways in which you can assess the performance of a model. If you have a classification model, you're looking at the number of misclassified, the fraction of mismatched or misclassified samples, which is given by this summation over here. The one is it's what's called an indicator function. It's that term over there. It's equal to 1 if your prediction of the class is same as the actual class. Then that's 1. Then that is 0. Otherwise, it's 1. Okay, so this essentially calculates the number of times your classifier misclassified data points. Now, if you have a regression problem, I'm going to get to regression a bit later. We're going to first cover classification, clustering, dimensionality reduction, and in the end, I'll get to regression. If you have a regression problem, you have a different error rate. But the point I want to make here is that when you train your models, or when you validate the models or test your models, you have to have some measure or some way of assessing the quality of your model. Right? So you have to. Typically, it's the difference between the predictions and the actual values that you've measured from the data. So there has to be some way of measuring the accuracy of the model. Okay, so let me draw something here. So in machine learning workflow, I mentioned this verbally yesterday and the day before. So the first step is to collect data, design and collect data. So design an experiment and collect data. And collect data. That's the first step. And then pre-process the data. So you have to process the data. Oh, thank you. pre-process the data, and then visualize the data. Okay? Thank you. This is step 1, step 2, step 3, and then you build a model. This is step 4. Then you look at the performance. Model performance. Let's say that's step 5. I did not really cover this topic, experiment design, and how do you design your, how do you choose your sensors, what kind of data do you have to collect. I sort of mentioned a little bit on what you can do to get good data, but I did not cover this. Okay? Often there's not a lot of flexibility in how in designing your experiments or collecting data, but if you have that flexibility, then it's a good idea to design your experiments and collect the right amount of data. If you have control over this, then you should make best use of it. And then the second step is the pre-processing part, okay, which is what we covered yesterday. We talked about data pre-processing, outliers, missing data, and other anomalies in the data. You want to fix all of that, clean it, and then once you have the clean data, the next thing that we need to do, which I'm going to focus on this morning, is visualize. Before some of you came in, I emphasized the importance of visualizing data because there are certain things in the data that you would be able to immediately detect by visualizing. Okay. There may be anomalies in the data or other features of the data that are unique to the system you're investigating. In addition to that, I'm also a firm believer in maximizing the value of these visuals before you use machine learning tools. Okay? So you want to get the maximum out of your data by simply visualizing it, even before you use any machine learning tools. Right? So this is a very important step. There are many different ways in which you can visualize data, and I'm going to show you some examples this morning. Sorry, before I get there, I wanted to show you something about training. So let me see if I can find it here. Okay, this is something that I drew on the board yesterday. When you get data, split it into training, validation, and testing data, and then you go to this loop, you train, validate, and then repeat this loop until you're satisfied, and then you test, right? I also mentioned, I think somebody asked me about the K-fold validation. I just wanted to show you what K-fold validation is. In k-fold validation, you divide the data set, the entire data set, into k equal sized parts. Then you leave the jth part, fit the model to remaining k minus one parts combined. Okay, so you just take one piece of your data, put it away, fit a model to the remaining data set. And then obtain predictions using the jth part, meaning you're using the jth part as your test data set. Now you repeat this 1 to 3 for different pieces. You have k different pieces of your data set. In every iteration, you throw away one piece, build a model. Okay. And then compute the average root mean squared error to check if the model is satisfactory. Okay, so you're not building your model once, but you're building your model k times. Okay, so every time you throw away one piece of the slices of data that you've created. So you split your data into k slices, you throw away one slice, build your model. Then you throw away the next slice, put the initial slice back into your data set, build another model. And for every model, now, which means you're going to get k different models, for every model you find the model error, find the average of the model errors for across all of those k data sets, and that is what is called k-fold validation. Okay. This approach is used to compare nonlinear different nonlinear models. Okay, so you let's say you have different types of nonlinear algorithms or models that you want to build on your data. And for each algorithm, you do k-fold validation, find the average of the model error across the k different models that you build, and then you compare these models across different algorithms. So the other thing that I want to mention here is there are two important properties of models, right? One is flexibility, and the other is interpretability. By flexibility, what I mean is the structural flexibility. So if you take a deep neural network has very high structural flexibility because you have millions and billions of parameters in a deep neural network. On the other hand, linear regression has very few parameters, and therefore the flexibility of a linear regressor is small. The interpretability of these models, when you have a linear regression model, it has a really good interpretability. You understand how different features are combined, etc. But when you have a deep neural network, the interpretability is lost because it's very complex. We don't understand what is inside. We don't fully comprehend how the deep neural network is working to give you the predictions that you're looking for. Okay. Yeah. Right. So you can build first principles models, right? That's not a problem. But not all processes are amenable to building high quality, high fidelity first principles models. What do I mean by that? There are, if you have a simple mechanical system, let's say a pendulum, you want to build a first principles model. There are very good physics-based models you can use on a pendulum, right? On the other hand, if you have a complex industrial process, say a distillation column or something like that, even there you can build first principles models. Well, the only question is, do they truly reflect the behavior of your system because of various disturbances and noises that may or may not be accounted for in your first principles model, right? So I think your real question is, do I use a first principles model, or do I use a database model, or do I use some combination of those models? The answer to that depends on how you want to use the models, right? And the quality of the model that you have. Okay, so I'll give you some examples. If you want a model to design a controller, a closed loop controller, right? For, let's say, not for set point tracking, but for regulatory control, right? You're probably going to be okay with a simplified data-based first order model. Okay? You don't need a complex, high-dimensional, nonlinear model for controlling your system, right? You'll be okay by approximating the original complex system with a simple linear first order model, right? So your controller will do fine. On the other hand, if you want a model for simulations and some sort of optimization of your product or product quality, etc., then you might need a higher fidelity model that incorporates first principles ideas as well as some database information, right? So it depends on the purpose. Where do you want to use this model? If it's a digital twin, of course you want a really high quality model, right? But a high quality model is not essential for achieving simple, good control performance, right? So depending on what you're doing, you have to decide. Then the other question is, do you want to use a first principles model, or do you want to use a database model? I think the answer to that depends on how good your first principles model is. So often we build for instance, if you take a distillation column, you can build a first principles model. It's no problem, right? But is that a good reflection of the real process you have? Or are you noticing significant errors between the model you have and the real process? If you notice significant errors, then you might want to upgrade your first principles model with a database model. Okay? So this is often this is what is called hybrid modeling. Okay? So the way this is done is you have your first principles model. Okay? There are different ways in which you can connect the first principles model with the database model. And the database model is typically built on the error between the first principles model and the actual measurements. All right? Yeah. Yeah. Right. Right. So the question is, the first principles models, they're typically based on principles, scientific principles, right? Physics, biology, chemistry, whatever, right? Often those principles don't fully explain real systems. Right? I mean, you can take many examples, even mechanical examples, like a robot, let's say, right? And robots have many joints, etc. You can most likely build some physics-based model that describes its motion really well. But in practice, there are errors that are very complex. Like maybe there is some friction, maybe the joints are not oiled well, and they don't move as expected. And maybe with time there is additional friction in the way they are moving. All of those things change the behavior, right? So if you don't have a sophisticated mechanism to account for those changes in your system, in the model, then your model behavior is going to deviate from the system after a while, right? Even if they are the same when you start using your system, but with usage, the behavior of these two is going to deviate. Then you have to go back and update your model. Okay. Often updating the real model is very time-consuming. It might take it might be expensive as well. Yeah. No problem. I can just keep speaking for hours without. So that's one reason, right? So even if you can describe your robot precisely with scientific principles, after a while you're likely to see this deviation. That's one reason. The other reason is there are systems where we don't fully understand the underlying scientific principles, right? So an example is especially the biological systems. I don't know if anybody here is working with biological systems. Say you're modeling a cell, right? Or you're trying to predict something related to the growth cells. Those systems are extremely complex. We have very few measurements we can take directly, and therefore it's almost impossible to, at this time with the knowledge we have, impossible to precisely develop a scientific based on physical chemistry underlying. So when you don't do that, you can, what normally happens is people build what are called lump parameter models or use order models. You build some models, and those models are not very accurate, but it's not, still the same behavior as the future. Now those models will deviate from the food system right off the bat, because that's the best you can do with the knowledge you have about the underlying system. So then those models will always be different. Now, in that context, can somebody here explain the difference between variance and bias? We talked about variance and bias. So what did you understand? What's the difference between variance? So when you have, and that has been this when you have a system, when you have a model that does not fully capture the dynamics, the behavior of an underlying system, then you're starting with a bias error. There's a structural mismatch between what you think your system is and what your true system is. There's always this structure. One way to think about it, I think, in mathematical terms, is you have a true system that is defined with some function defined by some function f. And you're assuming that this system, because you never know what this function f is, you're assuming that this is some with some input. And these two functions are not the same. F is not equal to 2. And as long as those two functions are not the same, you have a bias. You can make it small, perhaps, depending on the functions you have, the parameter values that you use. It might be possible to reduce the error between the two, but there's always going to be bias. Unless you choose accidentally or somehow you choose D also to be F, you can't make these two functions. If D is same as F, then you reduce your bias to 0. So with the example that I gave you, especially in biological systems, we don't know what this F is. We don't even have the scientific understanding of the system. The systems are really complex.
And often, through experiments, we come up with an approximation of this f, which is g, and therefore there's always going to be this error between the model and the true system. No matter what you do, how you generate data, what algorithm you use, you're never going to be able to you can reduce this error, but you're not going to be able to.
No, sir, it will come back. It will come back.
So you can never reduce it to zero. You can reduce it, but you can never reduce that. Right, so that's the bias. So with these systems where we don't have a full understanding of the underlying science, we will start off with a bias error. That's never going to go away. And when that happens, what you can do is your first principles model is only approximate and it has some bias. If you collect data, then you can find that bias, estimate the bias, and perhaps the variance errors. Then you build another database model to capture these errors. Database model, you don't need to understand the underlying science. Take data, try to build a model, and then you add the predictions of this model to the predictions of the first principles model to get a better estimate. Does it make sense? I can, if you want to understand this better, we can use an example. Right? So the example that I had yesterday was yt equal to alpha 0 plus alpha 1 ut plus epsilon, and the model you are assuming is yt equal to alpha 1 ut plus epsilon. The bias, this alpha 0 is the bias. No matter what you do with this model, you can never get rid of it. So my first principles model is this one over here. And we know that this model will always generate some alpha 0 plus another error, that is called E, the variance error, the bias error, and the variance error.
So let's say we measure this data, and we have many measurements of these errors. I can then build a model that approximates these errors, right? Which is what the database model would do. You approximate these errors, then you add them back. So whatever your prediction from the first principles model is, you add an estimate of alpha 0 plus E back to it, so that you get a much better approximation. So I think that answers your question. When you have biased first principles models, I mean, in practice, you can only guess that there is bias, right? Because the problem with modeling is you never know what this function is. You don't know. This is unknown. Except in some special cases, of course. There are certain types of systems where you can very precisely use scientific principles to approximate their behavior. Right? So a pendulum is a good example. You can write down kinematic equations very easily for a pendulum with high precision. But in most cases, you really don't know what this system is. You're always working with this one, okay? And this system that you work with will have some bias and variance errors. But you can eliminate them by building a database model on top of your first principles model. And those models are called hybrid models. There are different ways of building these, but this is a hybrid model. All right. For visual analytics, again, I'm going to use Professor Sri Shah's slides. They've done some very interesting work on visualizing different types of industrial data. So I'm going to focus on that next few minutes. You do not want to bury your data inside the algorithms. Instead, you want to display it. You can display your data effectively to convey information and patterns in your data. Often as humans, we respond much better to visuals than to some complex algorithms that we don't fully understand. So, and it also allows you, when you visualize data, it allows you to look at it cohesively and collectively. And on top of it, real-world data is not univariate, it's multivariate, meaning you don't have just one measurement. You have multiple measurements that you have to understand and interpret. Okay, so I'm going to show you some plots, high-density time series plots. This is, I believe this is from a refinery. There are about 37 different variables, and you can see the data. If there is an anomaly in the data, something that jumps out, you can very quickly identify it in a plot like this. Right? Instead of using perhaps a complex algorithm to process the data and extract that information. But if you plot it right away, you can tell if there is something going on with the data. Not only you can tell if there's something weird with the data, you can also tell where that abnormal behavior is occurring. Right? So it's the visualization is extremely important. This is an interesting example. I believe this is from a refinery, but I'll have to check. I think this is the example that I'm thinking it is. I believe this is from a refinery in Singapore. These are the tags. There are about 32 tags. Do you notice anything peculiar in these measurements? On the right side, you have the spectra of these time series data, but do you notice anything interesting in the time series data? Wait, sorry, which one? 21? 21 is low frequency. Okay, that's a good observation. So anything else? Do you see oscillations in some of these signals? Right. In fact, there are many signals there that are oscillating at very similar frequencies. So those oscillations are actually not noise. Noise often exhibits high-frequency oscillations. So there are some low-frequency oscillations. So take this one. These are all low-frequency oscillations. High-frequency noise is superimposed on those low-frequency oscillations. Okay. On the right-hand side, you see the power spectra. And the power spectra clearly indicates that there are some tags, some measurements, where they are oscillating at a certain frequency. So these measurements are all oscillating at the same frequency. So you have these 32 measurements. All of them are showing some form of oscillations. For instance, take this one. This is really clear. There's no noise in it, but you can see persistent oscillations. Right? And a spectral power spectral graph clearly shows which tags have those oscillations and at what frequency. Okay. So that's a very powerful intuition or observation about a process. Because I'm going to tell you, I'm not sure if I have. I don't have the slide that I was hoping to show you, but the point I'm trying to make here is this is from a refinery. These tags were the data, time series data was collected from a refinery, and we noticed very quickly just by plotting that there are many variables that are oscillating at the same frequency. And it turns out that in this particular example, I believe there was a sticky valve that was causing oscillations in one variable, one control loop, and those oscillations simply propagated through the entire system. So you have, I mean, you typically, in a refinery, you have multiple processes that are interconnected, right? You have upstream processes, downstream processes. If there are oscillations in an upstream process, those oscillations tend to propagate through the downstream processes as well. And that's what we're seeing. Now, just by looking at this graph, you can't tell where the problem is, where the oscillations originated, right? But there are some algorithms that we developed to isolate the problem. So those algorithms, machine learning algorithms, allow you to isolate the problem, but visualization helps you to identify the problem, right? Just by simply visualizing, you can tell that there are all these variables where that are exhibiting significant oscillations. Okay. Oscillations are not good. You have to figure out how to remove those oscillations. If they are localized and appear only in one variable, it's probably a problem you can you can ignore or wait to solve. But if these oscillations propagate through the entire system, then that's a big problem, right? So you have to figure out a way to stop those, prevent those oscillations. Okay. So that's one powerful example of how you can use visualization to solve a problem. Okay. You know, the other issue is, I talked about big data yesterday. There's just so much data out there. So you don't want to you don't want to be inundated and overloaded by Excel spreadsheets and numbers, right? So that's not going to be very helpful. So instead, we want to use proper data analysis tools to generate different types of plots and highlight important features in the data. Correlation plots are another type of plots that are very, very helpful. Has anyone here used these plots? These are very, you know, I find them very, very helpful. So you have some measurements on this side, measurements on that side. Each of these squares represents the correlation between the corresponding variables. Okay, so for instance, this is the correlation between, I think, variable 37 and variable 4. Those variables that have strong correlations are shown in red. Those variables that have mild correlations are shown in white or yellow. Okay. So plots like this help you to understand how different variables in your process are interacting. Now, sometimes, this is a temporal correlation plot, meaning we used the time series data for each of these variables to plot this correlation plot. You can also do a spectral correlation plot. You know, in the example that I showed you earlier, I mentioned that there are some variables that are oscillating at the same frequency. So those variables will all show up in a group in the spectral correlation plot because they all have same frequencies. This is an industrial case study. You have lots of different processes. Collecting the data, time series data, spectral data, power spectral correlation that puts all the variables with similar oscillations or frequency content together. And these are, through that process, we were able to extract the variables that have the same frequency oscillations. You can also do scatter plots. Scatter plots are also very helpful in understanding the correlations between different variables. So this is a histogram of this one variable here. Along the diagonal, you have histograms of the variables, and these off-diagonal squares represent the scatter plots, okay, between corresponding variables. This is also a scatter plot, but with more information. We are depicting different types of different categories of information in different colors. This is from, I think this data is from cars. MPG stands for miles per gallon, the acceleration, displacement of the engine, weight of the car, horsepower, etc. It's a similar plot to what I showed you earlier, but here we have, I believe, cars from different companies. These colors represent cars from different companies. This is what is called a parallel coordinate plot. Let me use this. That's a bit congested. Where so let's say take MPG, miles per gallon, for different types of cars, 4-cylinder, 6-cylinder, and 8-cylinder cars. And then you plot their MPG for each of those cars. There are three lines here, and you do the same for acceleration, displacement, weight, and horsepower. These are normalized data. That's why MPG is negative for some for certain types of cars. 3D plot of same data. That's also very helpful often. Next, in the next lecture, we're going to talk about principal component analysis. If you have highly correlated data, you will find that these data fall on a hyperplane within the three-dimensional space. Probability distributions, of course, are also very helpful. When you have data, you can plot a histogram of the data, look at the distributions to get the mean and the variance. That's one way of visualizing data. Box plots. What you see on the left-hand side is a scatter plot of the income of a sample group of people and the balance on their credit cards at the end of the month on the x-axis. That's the scatter plot. But you can translate that into what are called box plots, where you have whether a person has defaulted or not on the x-axis, no or yes, and then this box represents the variance in the balances, credit card balances of those who defaulted and those who did not default and those who defaulted. Okay. The right-hand side, the extreme right-hand box plot is for income. This is for income. That's the credit card balance. Wavelets are another useful tool for visualization. If you have time-varying signals where your frequencies are changing with time, wavelets are a great way to visualize the data. This is an interesting plot. It's called a high-density alarm plot. On the x-axis, you have time, and on the y-axis, you have various alarms. And you're counting the number of alarms on each day. If you have 0 alarms, then you don't show anything. If you have lots of alarms, you show it with those red bars. Okay. So a plot like this can offer so much value, right? For instance, if you immediately realize that tag 192 is showing a lot of alarms. You can also see that there are some tags. Tag 102 is experiencing frequent alarms. This sort of information is very easy to see, visualize using a high-density alarm plot. I really like these plots, these circular plots. So on the outer circle, you have the time of the day. It's like a clock, and every circle inside that represents a day. So this is for data from January 1st, 2017 to March 31st, 2017, right? And every circle inside represents one day. And these red or purple colored bars, they represent the duration of alarms. Okay, so for instance, on this day at 8 o'clock in the morning, there were some alarms. So this clock-based depiction of alarms is also very useful, because you can see if there are certain alarms that are appearing at a certain time every day, right? Or if you can see any patterns of that type very easily in a class like this. Yeah. Yeah. Sorry, where are the two bars? This one and this one? They are on different days, yeah. Yeah. So each circle is one day. Okay, so this is a similar plot. So green over here, I think, I'm not sure what the color coding is, but the green, I think, represents there are fewer alarms or something like that. We have yellow, there are different levels of alarm flooding. This is a similar graph, but it just shows the number of alarms in each hour of the day over a certain period, few months. I want to show you a couple of examples, a couple of other examples of where we've used visualization to solve interesting problems. Okay, so this example, it's a lime kiln, a schematic of a lime kiln. Have you heard of lime kilns? They're used in cement plants. Yeah. They're also used in I think other industries. So they generate a lot of greenhouse gases. Okay, and apparently they generate about greenhouse gases that are equivalent to 300,000 cars running on the road for a year. Right? So they're massive, right? Really big. But what happens is, as you run these lime kilns, they grow what are called rings inside, right? And these rings, when they form inside, it reduces the efficiency of these lime kilns. At some point, they have to go and turn off, shut down the kiln, go inside, and clean them. So in this example, what we did was So we installed those infrared cameras on the line kill. These are, I think there were about 30 different infrared cameras. And those infrared cameras generate images. We stitched those images together and presented them in a way that operators can see. So this is the inside of the lime kiln. Okay, so inside, when it's hot, when it's not hot. And these sections represent the sections that the infrared cameras are monitoring. So we took those images, stitched them all together in a way that allows operators to understand if there are rings growing inside the lime kiln, right? To get some intuition into that. And this was a very simple idea, but proved to be very effective in monitoring the system. Okay, so this is one example of very simple data visualization. This idea was turned out that a company is trying to sell. You would think it's just so simple. I should have another example. Sorry, maybe I pulled the wrong slide. Let's see. This one. Yeah, so this is another interesting example. I know some of you have heard of model predictive controllers, right? Model predictive controllers are these complex optimization-based controllers. It's difficult to provide intuition into what those controllers are doing. And I mentioned this, I believe, yesterday or the day before. So we came up with an interesting way of visualizing the gains in the model predictive controller. It's basically a color map of gains in the model predictive controller. And this is a map of the constraints that are active. Okay. Yeah, I apologize if you don't know what model predictive controllers are. So it shows which constraints are active and at what time. Now, operators and engineers can look at this and gain some insight into how their particular model predictive controller is working. So there are many simple ways of visualizing data that helps you gain insight into the data, even before you